We are.
Or should we align?
Are the others connected?
The others are all connected. Skip like the 3 feet. Yep, definitely.
Okay. So, dames en heren, ladies and gentlemen, geachte collega's, dear colleagues, I hereby formally open this session and I welcome you all to the public defense of Jan Philip Sindel. Jan Philip Sindel has presented to the faculty his PhD thesis on the topic Cloud Formation in Exoplanet Atmospheres, Nucleation of Small Molecular Clusters, in partial fulfillment of the requirements for obtaining the degree of PhD in Science Physics. I should just add that this is a dual PhD, so the rules are a bit different than usual, and this is a bit of a strange defense in the sense that you can confirm, yes, that Jan Philip Sindel has already had the preliminary defense in St. Andrews. And today, the public defense will occur. Usually, we have both defenses in Leuven. But all of the jury members are here or online or excused. And Jan Philip shall now publicly defend his PhD thesis. You are invited to give a presentation of about 45 minutes about your work. And afterwards, I will first introduce the examination committee, and then the committee will ask questions and discuss your work with you. The floor is yours.
Thank you very much. I hope everyone here and online can hear me. Very well. So, as has already been mentioned, you should sit over there on the side so the camera or the jury can see you. Like the last previous. Thank you. Sorry. All right. So, as has already been mentioned, I've been doing my PhD at 2 different universities, here in Leuven at the University of St. Andrews. And you might not be able to tell today, but usually, both at St. Andrews and Leuven, it's very easy to do a very practical, very direct examination of clouds. I'm however not interested in clouds on Earth. I'm interested in clouds anywhere. Move now to Graz. Study of clouds there, a bit more theoretical. We're talking about exoplanet atmospheres, but in order to talk about exoplanet atmospheres, we first need to talk about exoplanets. So exoplanets are planets that orbit stars that are not our sun, that are outside of our solar system. We so far know of 5,000 confirmed exoplanets. And of all the planets of which we know the orbital period and the radius, there's a diagram plotted here. So this is the orbital period, aka the time it takes for the planet to go once around its star, and the planet radius in Jupiter radii on the y-axis. So if we, for example, look at a planet that has the radius, that of Earth, which would be roughly here, and an orbital period of 365 days, then that would be Earth. So as you can see, we have not really found anything that is like Earth. We have found some things that are further away from the star. We have found some things that are smaller, but nothing. It's a combination. When we look at exoplanets, especially at exoplanet atmospheres, what we're interested in is big targets. We want big targets. We want to be able to observe them often. So we will be looking for something that is high radius, low orbital period. So great enough that there's this crowd of planets up here, which are larger, as large or larger than Jupiter, and very close to the planet. Therefore, they're quite hot. So they're called hot Jupiters. When we talk about exoplanet atmospheres, first question is, why do we want to look at exoplanet atmospheres? On left here, you see a rough sketch of how a planetary system forms. So we start with a huge molecular cloud that collapses onto itself gravitationally, then you get a protoplanetary disk. In the middle of the disk, the star forms, and then everything around that accretes, forms pebbles, planetesimals, and in the end, planets. Now, this entire process is being modeled a lot, and what we want to understand is how chemical compositions of the original molecular cloud influence the final chemical compositions of the planets, and how that all works together. So in order to look at the chemical composition of a planet, especially exoplanet, we can't just go there, take a sample, come back, analyze it in the laboratory. We need something remote. We need to look at something that we can see, which is the planet's atmosphere. So if you look at this, if you look at a planet, I chose Jupiter for obvious reasons. And in this atmosphere, it has tons of different molecules, tons of different molecular species. And these are the things that we want to detect. These are the things that we want to observe. So first of all, the question is, how can we determine, just from observations from afar, what molecules, what chemical species we see? We do that through something called spectra. So in general, if you have light, just straight red light, and you use prism to break it up into its different colors, wavelengths, I'm going to use those terms pretty much interchangeably, pretty much get a flat spectrum. Now, if we take the light and shine it through a box of oxygen molecules, you can see here, and then in the prism, we can see that some of the colors, some of the wavelengths of the light have been taken away by absorption of the oxygen of this gas. So we have absorption lines that originate from this gas. Now, if you use nitrogen instead of oxygen, these absorption lines are different, which means that the spectra we observe directly correlates to the gas it has passed through. So this is how we can, even from afar, by observing the light, tell apart different chemical species. Now, of course, we're not observing light bulbs, we're observing exoplanets. And for that, I want to first look at how most of the exoplanets we've discovered were detected, and also how we can observe them, which is during a transit. Transit happens when the planet, as you can see here, will it start moving? It will. Excellent. Passes in front of its host star. And if you observe the brightness during that time, you will observe a dip in this brightness. Of course, a little bit of the starlight is blocked. It won't pass. It doesn't pass through the core of the planet. However, what it does pass through is the atmosphere. So if we observe the star with a telescope in Earth, and this light has passed through the atmosphere of an exoplanet, and the light that we now collected with our telescope, we use a prism again to put it into its parts. We have a spectrum that is to some degree impacted by the chemical species that are in the atmosphere of this exoplanet. Now, in an ideal scenario, say we have a space telescope, so we don't have anything, any atmosphere blocking us, and we have a pretty good state-of-the-art, pretty new space telescope. That is pretty much an ideal case scenario. So WASP-39b, which is a hot gas giant exoplanet, to avoid saying Jupiter, was observed with JWST, and these white dots are the data that make up the resulting spectrum. And as you can see, they marked all of the features. You can see carbon dioxide feature. You can see a feature from water. You can see another carbon dioxide feature, unexpected sulfur dioxide feature, and all of these things. Great. So if we look through the atmosphere, we have absorption lines. It's excellent. It's exactly what we want. Now, sometimes we don't get what we want. Sometimes there are clouds. And if you've seen clouds outside, clouds are white. Clouds don't have any specific color that they take away or put in there. Pretty much a gray opacity source. So what happens is if the light passes through there, it doesn't get changed in any particular direction. The spectrum that we earlier saw just has lots of ups and downs. As in this measurement of GJ1214b, just becomes flat. Like, for example, if we expected to observe the spectrum of the planet, at solar metallicity, so with the same amount of chemical species that the sun has, we would expect it to go quite a lot up and down. But what we measured was that it's very flat. So we know that clouds impact our observations of exoplanets. So we need to understand how these clouds form, where they form, and the processes that are behind that. So if we talk about cloud formation, it's something that happens pretty much at the top of the atmosphere, so around here. And on Earth, it's pretty simple because all of our clouds are made of water. You get small condensation seeds, because you have water that is supersaturated, which means there's more water vapor than would be stable in equilibrium. So the water wants to condense. And in order to condense, it needs small nuclei, small surfaces to condense on, like small dust grains or soot from volcanoes, salt crystals from the ocean. There's tons of stuff in the atmosphere that can act as a nuclei and on which the droplets can condense. Now, we're in a gas planet. We don't have a surface. We need to get our nuclei somewhere else. So basically, this is where cloud formation happens. And in order to look at it more in detail, you have the top of the atmosphere, and the first thing that happens is a process called nucleation. We tuck individual molecules together, we grow them in order to get a small surface, in order to get something that the rest of the chemical species can condense on. So that is what comes out here, which is a cloud condensation nucleus. Now that we have a surface, everything else that is supersaturated, which in hot Jupiters is usually metal oxides and other stuff that we would never imagine clouds to be made of, but that's the stuff that condenses. And then everything is being dragged down by gravity because it's heavier than the environment. And in the next step, there's a lot of collisions in between these cloud particles. So as soon as we pretty much have a cloud, like this is an individual cloud particle made from different materials. Then it gets, they have different collisions. Some of them stick together, some of them fragment. And as soon as you get low enough in the atmosphere, it becomes too hot for these cloud particles to be stable. So what happens is they evaporate again, they go back into the gas phase, and there are convective and diffusive mixing of these lighter molecules back up. So you, in the end, have a cyclic process. So which is at the top, basically the top layer of the cloud is defined by how far up the nucleation can happen. The bottom layer is defined by the thermal stability and when that stops. So as you can maybe tell from the start of the title of my presentation, my interest is in this very first step in the nucleation of the small molecular clusters in order to form our condensation seeds. So if you look at nucleation, we start with individual molecules. Individual molecules are called monomers. Also, going to use the word a lot, so should remember that. So if we then, if some of them meet each other, stick together, boom, we have what we call a cluster of size 2 or a dimer. Now we can add a third one, and we have a trimer, cluster of size 3, and that continues. Of course, this is a very, very approximate graph. Like these things are about a nanometer, half nanometer in size. That is nothing that can count as a surface for condensation purposes. We need to go to very large numbers, large cluster sizes. And another thing we need to do is we need to be able to quantify that. We want to put this in models. We don't want nice graphics, we want numbers. So unfortunately, we need to use math. This is modified classical nucleation theory, and this is the equation that gives us the nucleation rate. So the amount of seed particles that we form. Now, this is pretty big, so I just split it in a couple of pieces. This first part is the monomer number density. So basically the answer to the question, how many molecules are there? How many molecules do we have to build our seeds? Then below that is the growth time scale, which basically answers the question, how fast do they grow? How often do they collide, stick together, etc. And the entire term back here, I just call the stability term, because that answers the question, how stable are the clusters? And good thing about the first two is we know that just from the gas. We know the pressure, we know the temperature, We can use that to get ideas of the monomer number density. So the thing we don't know from the gas directly is back here, is the red term, is the stability term, because that requires knowledge of the clusters, especially final term here, which is the Gibbs free energy. Now, I focused my work mostly on titanium dioxide, TiO2 as a seed, because TiO2 is very refractory. It's stable at very high temperatures. It's abundant enough to be a good candidate for a cloud condensation nucleus. So we start with the monomer. So we have an individual TiO2 monomer, and we know what a dimer looks like. We know that these are two, but it could also look like this or like this. And then when we look at the trimer, when we look at clusters of size 3, there are a lot of different geometries that these clusters can have, a lot of different isomers. And we want to know which ones are the ones that partake in this nucleation process. So our assumption is that the energetically most favorable cluster of every size is the one that's participating. So we need to find that. For one, that's no problem. We know the Gibbs free energy from experimental measurements. But then as soon as we get to size 2, that already gets more difficult. We need more other methods in order to determine that. And we can see, yes, this is the most stable one because it has the lowest Gibbs free energy. And for all of these, it is this one. But you can see that some of them are incredibly close together. 1814, 1815, like very close together energetically. So in the right they could exist in parallel if the conditions are right. Now, okay, we need to find the energetically most favorable cluster of every size. So how do we do that? We do that by looking at the energies, and in order to get the energies, we need to look at the interactions between all the elements, all the atoms within our molecule. And for that, I created something I call the funnel, which basically takes a lot of candidate geometries, like just geometries with the right amount of titanium and oxygen atoms, and then uses 3 different methods to describe the interactions within them in order to, in the end, get to the global minimum and find out which geometry is the correct one. So I'm going to go through the 3 methods real quick. So first of all, we have the force fields. They're very simple. So you look at the molecule. It's made up out of atoms. Each atom interacts with another atom, and their interactions are only described with the electrostatic Coulomb force and the van der Waals forces. So for two atoms, A and B, the only interesting aspect is the distance they have between each other. Everything else is parameterized by this force field. So we have A, B, and C, which are the Buckingham parameters, which describe the van der Waals force, and in the end, the Coulomb term from the charge. And so these are only 10 free parameters. So I parameterized this for these purposes myself, and used that in order to relax the candidate geometries. So the idea is that the things we create, they're not physical. We want to put some physics into them to make them into something that resembles a cluster. And that's what force fields are excellent for, because with very little computational power, they can relax these clusters into something that is in the local energetic minimum. Now, if we want to describe the energies, this is too approximate. For that, we use DFTB. DFTB is short for density functional base tight binding. It's more computationally expensive, but the idea is it is more accurate because in addition to just looking at individual atoms, it also looks at the valence electrons. So like the outermost electrons of all of the atoms and their interactions with each other, because atoms are not just a charge, but also have lots of electrons that take part in bindings and all the interactions. So it's important to describe them as well. For that, it's a bit of a black box because the parameterizations are very complicated, but there are 3 parameterizations available that describe the interaction between titanium and oxygen, which I'm interested in. And out of the 3, I chose the mass guy file because it performs the best. So finally, DFT, or density functional theory, is incredibly computationally expensive. What we're basically trying to do here is we try to solve the Schrödinger equation. We try to get all the interactions between all the electrons in the entire molecule, which is a lot, and from there get the energy. So for that, you need parameterizations in the form of a functional and a basis set, which would go over the frame of this presentation to completely explain. But in the end, there are a lot of them. I tested 129 combinations. And by tested, I mean we have the experimental values for the TiO2 monomer for an individual molecule. So I calculated an individual TiO2 molecule with all of these combinations and saw which one best represented the experimental values that we know. And in the end, I ended up with the V3 functional, the CC PVTZ basis set, and G3BJ empirical dispersion, which very closely resembled the experimental results for the monomer. Now, basically, we have everything we need, except we don't, because in order to, we have a funnel that works. All of these methods are calibrated. Now the question is, how do we fill it? How do we get our candidate geometries? For that, there have been studies been done into TiO2 clusters. So I devised 4 different methods to create these clusters. First of all, I split them into 2 size categories, small and large clusters, smaller size 3 to 7 and larger size 8 to 15. Smaller clusters have less candidates created because it's the parameter space. The amount of configurations possible is just not as big as for the larger clusters, 8 to 15. I ended it at 15 because computational cost beyond that just goes absolutely bonkers, and it's just not feasible. So the first method I have is a random method, because we know what the monomer looks like. It's just these 3. So we can just attach another monomer in a random direction. And all of these examples are for a cluster of size 7. So this is size 2, then we had another one, 3, 4, 5, 6, 7. Excellent. We do that 1,000 times for each small size and 5,000 times for each large size. Get a lot of geometries that have the right amount of titanium and oxygen, but obviously no physics in them. Another maybe more physical approach is a known plus 1 method. So basically, we take a cluster that's already known from the literature, and we just add another monomer. We have a monomer. We have a cluster of the size that we want. Perfect. The third method is the mirror method. Basically, what the idea behind that is nature, like a lot of the larger clusters we see, are symmetric. Symmetry is often observed. So we want to create symmetric clusters. So we take a known cluster, we mirror it, and if we now have an uneven number that we want, we just add another molecule in the middle. Great. And the final one is because especially the random method creates quite sprawly with like long and elongated clusters. I wanted something that creates more compact ones. So we take, in this case, 7 points, 7 monomers, distribute them on a sphere. 4, 5, 6, 7. I promise you, they're on a sphere. It's not easy to show 3D. And then we rotate them all inwards so that it is nice and compact. So in total, that makes 90,000 candidates across all the sizes that we're looking at. And so I adapted the figure for the funnel a little bit because this is more what it looks like. And now we're going through it. Now we're dropping them all into the force field. So what the force fields do is, as I said, if you remember, this is the randomly created structure from earlier. With a force field, it relaxes into a local energetic minimum. This is something that is stable, at least at the force field level of theory. And then now we have 90,000 of these. So now we want to know which one of these are actually any good. So we use DFTB to do our first energetic ordering and to see if we have any global minimum candidates. Global minimum candidates are clusters that are lower in energy than the currently known global minimum, so the most energetically favorable cluster of a certain size. So here, for all the sizes, you have the amount of global minimum candidates we found. So you can see for most of them, we found some that were, in DFTB, better than the ones we knew. And in addition to that, I also calculated 10 isomers, the 10 next best isomers for each of these sizes. So those were a lot of DFT calculations that were done on the HPC Kennedy cluster in St. Andrews. And yeah, great thing is from that, we get our Gibbs free energies, for example, for this cluster of size 7. And we also get a lot of info about the isomers that they have, which is going to become interesting later. So yeah, we have the data we need. We have the individual molecular data. So now we look at the results. We have the literature clusters. We have the global minimum clusters for sizes 1 to 12. We replicate them. We didn't find anything better except for size 13 that we found. This cluster that was not previously known and is energetically more favorable than the one previously known. For size 14 and 15, we didn't cover the parameter space enough to find the literature clusters. But yeah, I assume it's mostly due to the mirror method being incomplete. Because it only went to size 6, and we need size 7 to create 14 and 15, and that method was most successful for larger clusters. So in total, we have 123 geometries and full thermochemical data for all of these isomers of these different sizes. And now we can use that to go back to math. So in modified classical nucleation theory, you actually don't use individual cluster data directly. You still approximate the entire cluster data through a single term, which is the surface tension. The surface tension is over here. You can think of the surface tension as if you have like a big block and you break it apart, you're going to increase the surface. And the energy per surface you need, the energy you need to break it apart in order to increase that surface, that is what characterizes the surface tension. So basically, it's a measure of how tight, how close together these clusters are. So the surface tension is over here. And you can see you can use that to basically solve the entire equation, because we know this from the gas, we know this from the gas. We can use this to solve for n star. We can use this to solve for the final term. Everything else is known. We can finally do nucleation rates. First, we need to find out what our surface tension is. For that, we can thankfully fit this very simple equation. We know all of the Gibbs free energies for clusters of size n, We know the Gibbs free energy for the monomer. We know it for the solid phase. So the only variable in here that is unknown is this theta. So we can directly get the surface tension by fitting the data we have to this equation, which is more elegantly shown here. So there was previous data on these clusters up to size 10 by Lee et al. And I compared my results in blue to theirs in orange. As you can see, the resulting surface tension differs by about 40%, with theirs being quite a bit higher. So now the question is, okay, great, new data does make a difference here. How do we now get the nucleation rates? And in the end, we want nucleation rates in the atmospheres of our Jupiters. So I need to make a small deviation to pressure temperature profiles and terminators. So pressure temperature profiles are how we describe exoplanet atmospheres, because as I said, we need to know information about the gas. We need to know its pressure. We need to know its temperature. So at a certain point in the atmosphere, every pressure, so low pressure is high up in the atmosphere, high pressure is low down in the atmosphere, has a corresponding temperature. So we start with a very isothermal at around 700 Kelvin, and then it goes up in temperature the further we go down in the atmosphere. Now, of course, exoplanet atmospheres are not homogeneous, so we're mostly interested in the parts we observe. So these are called terminators, because we have our star, and our planet always has the same side pointer to its star, because it's tidally locked. And so we have an eternal day and an eternal night side. And between those eternal day and eternal night side, we have the terminator. And since our planet is technically still rotating around itself, the morning terminator and the evening terminator, and directly underneath this is the substellar, underneath the sun, is a substellar point and the antistellar point on the other side of the planet. Now, this pressure temperature profile is one from the morning terminator. So what I did was I went along the pressure temperature profile at each point. I calculated the pressure, the temperature, and using equilibrium chemistry, the monomer density, so the amount of TiO2 molecules we would find. I then used that to finally calculate nucleation rates. We got there. So if you look here, we have different temperatures and in this atmosphere, and the nucleation rate on the y-axis. Again, with the surface tension from my work in blue and with the surface tension from Lee's work in orange. So you can see that with the new data, with the new surface tension, we actually have roughly an order of magnitude high nucleation rates across the board, and also it gets nucleation rate becomes inefficient at slightly higher temperatures, which would extend the cloud cover a little bit lower in the atmosphere. However, nucleation rates with modified classical nucleation theory that again reduces all the nice cluster data we have into a single variable, maybe with an oversimplification. So maybe let's try non-classical nucleation theory. Non-classical nucleation theory, nucleation rate looks like this. In the end, the main difference is the time growth time scale, same thing as before, but now we have the monomer density, the number density of every cluster size in here, and these are explicitly calculated from their Gibbs tree energy. So now we can use the full cluster data that we have created to calculate nucleation rates, and let's see what difference it makes. So in green, it's the same as the blue before. That's the one with modified classical nucleation theory. And now in blue and orange is non-classical nucleation with both my data and Lee's data. As you can see, over most of the temperature range, it doesn't really have an impact. The only impact it has is that it actually becomes inefficient at lower temperatures, which in the end then rises the lower boundary of the cloud layer in our atmospheres. So this new data has made an impact on where the clouds, how far the nucleation rate can extend into the atmosphere. Now, this is all very nice because it's very theoretical, but now I also want to talk a little bit about what we can see. So I'm going to talk a little bit about vibrational spectra. So again, we have our light source, and now we shine them through some TiO2. And the thing about TiO2 is it has vibrational modes. Like the things that cause the absorption lines are vibrations in the molecule that are energetically identical to the wavelength they absorb. So these clusters, these molecules, they extend, they wiggle around, and these modes correspond to absorption. So you can see that wonderfully. You have an absorption mode here, a smaller one here, and a tiny one here, if you're going to believe me. Of course, this is just these correspond to the three modes that are shown here. If you go to larger molecules, you will have more modes. So, for example, this is a molecule of a cluster of size 15, and that's just one of its modes that it has. And you can see it has many more modes. So we want to look at the different sizes and how their spectra compare. So I extracted all the vibrational spectra from all the DFT calculations that I did, which thankfully was basically a byproduct. And here we're looking at a pressure of 1 bar at a temperature of 1,000 Kelvin. And we're comparing the different sizes and what their spectra look like. You can see the wavelength region is from 5 to about 30 micron, which is picked intentionally because that is round about the furthest extent of where GWST's MIRIC instrument can go. And we can see we definitely have a big difference in what the spectra look like between smaller and larger clusters. We have cluster of size 1, it's just basically a single bump here. Cluster of size 2 has a couple of bumps, and then as soon as you go to 10 or 15, you basically have almost a forest of lines in this area. What's also very interesting is that not only different sizes have different spectra, but also different isomers of the same size. So if you compare now the n equals 2 isomers, so clusters of size 2, we know 3 different isomers. And we see, for example, they have this mode is something they roughly all have in common. So in the global minimum, in the first isomer, it corresponds to this very asymmetric kind of a breathing mode, which in the third isomer is kind of reproduced in it's a very asymmetric movement. However, there's this peak at around 12 micron that happens in the third isomer that can't be replicated by the second isomer because the geometry is different and the first isomer doesn't have an equivalent mode. So now we have cross sections. Cross sections are measured in square centimeter per molecule. So in order to know how much light actually gets absorbed, we need to get a total absorbance. We need to know how many molecules there are. So for that, we need abundances. In order to get these abundances, what I did was I took all of the thermochemical data that I had for all of the isomers and implemented them into an equilibrium chemistry code called ggchem. And then I let it run at different pressures, at different temperatures to see in chemical equilibrium what is the most abundant titanium-bearing species. And that is something you can see here color-coded. So you have temperatures from 300 to 3000 Kelvin, pressures of 10 to the minus 2 to 10 to the minus 10 to the 2, 100 to 10 to the minus 15 bar. And we can see which is the most abundant titanium-bearing molecule. So let's start over on the left. We have orange. It's called TI15030. So it's a cluster of size 15, so the largest cluster we're looking at. The 0 means it's the global minimum, which so it is the most energetically favorable cluster of that size. And pretty much everywhere this is, especially when it's a little bit colder, that means that the solid phase, like just pure solid TiO2, because these are all gas-phase molecules, is probably also stable. So if I had data for TI16, TI17, etc., that would probably they would probably be here as well. So the next part is, in my opinion, one of the most interesting parts. It's this green area, where the most abundant titanium-bearing molecule is not the largest cluster, but the second largest cluster, TI14028. So what that tells us is there's something that is inhibiting that growth to size 15. So size 14 is the most abundant cluster here. So even if all of the stuff that's in 15 goes to 16, 17, all the way to the solid, there could still be this TI14 clusters here that induce absorption. Then up here, when the temperature is a bit too high and the pressure is a bit too low, the larger clusters just become unstable. They just don't really form. So there's an area where TiO2 is dominant. And then if you get too hot, TiO2 no longer is the most stable titanium oxide. It just becomes TiO, which is in all this yellow part of the graph. And then if you keep heating up and keep lowering the pressure, you lose your oxygen, and in the end, you even lose some electrons. So you go to Ti and then to Ti+. Now, what's interesting here is the pressure temperature profiles that I've overplotted. I'm looking at two different exoplanets. It's WASP 96b, which is a warm/hot Saturn/Jupiter, and WASP 121b, which is an ultra-hot Jupiter. So for both, you have the morning terminator in black, the evening terminator in white. So let's start with WASP 96b. You have the morning terminator, overall quite cold, 500 Kelvin, and then if you go low into the atmosphere, it gets a bit hotter. And the evening terminator, a little bit hotter, like around 800 Kelvin, and also then at the bottom goes down towards, the temperature goes up. So basically, what I do is I follow along these lines, along these temperature pressure profiles, and at a given step, I take, so at 10 to the minus 12, 10 to the minus 8, 10 to the minus 4, and 1 bar, I compute the abundances of all isomers, of all clusters, and get their cross-sections to multiply all of that in order to get a total absorbance. So what all the clusters at this pressure level absorb. So we start with a WASP-96 B-like planet. So the stellar temperature is around 5,600 Kelvin. It has an effective temperature of 1,200 Kelvin and log G of 3. We compare the morning and evening terminator. These are a little bit confusing because the lowest spectrum is highest up in the atmosphere. True. Oh, that looks good. All right, then I first need to. No. That looks good, right? Yeah. All right, perfect. So as I was saying, these graphs are a bit counterintuitive because the top of the atmosphere is actually at the bottom of the graph. So you see 10 to the minus 12 bar, so very low pressure, which means very high up in the atmosphere, is pink down here. The reason for that is, as I said, this is total absorbance. So it is the cross-sections multiplied with the number densities. Of course, the higher up you go in the atmosphere, the lower your pressure, the lower your number densities, so your total absorbance is way lower. Now, what I find very interesting here, and I hope you'll agree, is differences between the morning and the evening terminator in their spectra. Because, for example, for the morning terminator, that, as we said, is a lot colder, you basically are missing this little, this peak for at the top of the atmosphere and pretty much all the way to 10 to the minus 4 bar. So what that peak corresponds to is the TI-14028 cluster. That's a cluster of size 14, which to which area of dominance the evening terminator is much closer than the morning terminator. So what we have is a pronounced difference in the contribution to the spectrum by these clusters in a very different way between the morning terminator and the evening terminator. So in the evening terminator, you have this additional absorption by TI-14, which the morning terminator, you don't. Now, if you look at a WASP-121b like planet, which is much hotter overall. Like it has an effective temperature of like 2,200 Kelvin. And you can see that the morning terminator has this area where it's fully in the TI-14 dominated phase, and then at the end, pretty much, yeah, as the oligo gets very hot as you go deeper into the atmosphere. Whereas the evening terminator is way hotter and is often even in the TIO dominated sphere. Thing is, I didn't look into TIO, I looked into TiO2, so I have no idea on the absorption spectrum of TIO. So that is obviously missing from the next slide. However, you can still compare the morning and evening terminator, but for the evening terminator, as you can see, except for 10 to the minus 4 bar, which is about here, where it's in the TI-14 dominated area, this spectrum is so dominated by TIO and a little bit also in TiO2 that you only see the TiO2 feature and nothing else. And in this, in the 10 to the minus 4 bar, you see a very prominent, this second size 14 peak, in addition to the rest, which is pretty much just a combination of size 15 and 14. And again, we have at several pressure levels, especially at 1 bar and at 10 to the minus 8 bar, in this case, severe differences between the morning and evening terminator, because at the morning terminator, it's cold enough for TI-14 and TI-15 to exist, whereas at the evening terminator, it is just too hot. So, hey, if we're lucky, this could be observable. So yeah, this is pretty much all I did when it comes to look into cloud formation exoplanet atmospheres with a focus on the nucleation of small molecular clusters. So in the beginning, I developed a method to find small clusters and their properties, the little funnel that I love so much. And we see that the updated cluster data that I create in this funnel change nucleation rates and also the temperature limits that they have. Then I extracted a vibrational spectra for all of the clusters that I generated. And I've shown you that there's a difference in the cluster spectra between the terminator, between the morning and the evening terminator. And hey, if we're lucky, this could be, like, we still need to do more studies on that, but let's see, maybe this turns into something that we could observe. And that's it for me. Thank you so much for your attention, for watching, and yeah, open for questions. Thank you.
Okay, thank you very much, Jan Philip. First of all, let me introduce the members of the examination committee. Maybe you could bring the online. Yes, there they are. So we have two external members, Yamila Miguel from the University of Leiden. We have Alex Scholz from the University St. Andrews. Then we have here David Gabrecht from the University of Gothenburg. We have two internal members from KU Leuven who are not here today, Jeremy Harvey from the Department of Chemistry and Christopher Wolkens from the Department of Astronomy. Then also online we have Christiane Helling from the University of Graz, who is co-supervisor of the PhD. We have here Léne Dessin, who is from KU Leuven, supervisor of the PhD. And I am Jérôme Leroux. I'm the chair of the examination committee. So I would like first to start with Yamila Miguel. You have questions that you would like to discuss with the candidate?
Sure. Can you hear me?
Yes.
Yes.
Okay, great. So first, I would like to thank you, Jan Philip, for a really nice presentation and thesis. I already asked you many questions in your Viva, so I will just select 3 today, and those are related to real exoplanets. So my first one is, in real exoplanets, it is likely that more than one species exists. So how does this affect the formation of TiO2 clusters? So basically, how can you use your method to calculate what happens in real atmospheres?
So I mean, to a degree, I'm going to say I account for that because in the end, when I calculate how much TiO2, how many monomers there are, how many molecules we have to start from, that also include, like, that is not equilibrium chemistry run with only titanium and oxygen, but that has all other species as well. So all other species that would be stable, that could basically take oxygen away from TiO2 and make it not exist. Those also all exist in the same. Those are all part of the mixture that I use to calculate the abundances. So I would say that, like, there's no if there were other species that could steal, for example, oxygen away from TiO2, those they already did that. Like, oxygen exists in these calculations as well, like molecular oxygen and carbon dioxide and all the other stuff. Like, this is really the amount of titanium dioxide that exists in chemical equilibrium with the solar composition.
Okay, thanks. And then if we move to the spectra calculations, you show the spectra of titanium-bearing species, but again, in a real atmosphere, those features might overlap with features from other molecules. So the question is, do you know if some of the features that you are showing here will be observable in, for example, let's say a solar composition atmosphere like the one you calculated the abundances?
I can... What I can't, we haven't looked at at how this absorbance works in a fully modeled atmosphere with other species present and their absorption and everything. So what I can say is, for example, a feature. Wait, can I? Like, pretty much this feature that has been very consistent throughout all of it, which is at around 10 micron. There's also a silicon feature like SiO2. That is at around 10 micron. So yeah, that would likely overlap. But maybe this little one here at 11-ish for the Ti14 can save us. I'm not entirely sure. I don't know a lot of the other absorption lines for the most popular, for the most abundant species by heart. But like, there will definitely be some overlap. But just got to be lucky.
So more like a combination of different features that are unique for this one, you think? Okay.
Yeah.
And then my very last one, and then I let others to ask questions as well. If you would meet me, let's say, in an elevator, and you have 30 seconds or so to convince me why I need to read your thesis, what would you tell me?
I assume this is an elevator at an astrophysics institution that deals with clouds, because otherwise I don't think I could convince a random person in 30 seconds. I would say, hey, we need to, my thesis shows you that using very intensive methods to get the data, to get this updated cluster data, to get thermochemical data actually makes differences in the models, makes differences in where the clouds can form, where the nucleation rate is effective. So please fund my research.
I like that you were speaking fast, like it was really an elevator. Okay, thank you so much.
Seconds.
I don't have any other questions.
Okay, thank you so much. Next up was Alex Scholz, but he unfortunately had to, you saw the message that flashed on the screen, but he sent me an email saying that he was happy with the changes that you made and that you already had ample opportunity to discuss your work during the first defense. And I should take this opportunity myself to mention that usually the jury is the same for both defenses, but here, in this very specific case, it is not. So I was not there for the preliminary defense. Then Dessin was not there. David Gobrecht was not there either. So this is a bit of a strange situation. So next, I will ask David Gobrecht if he has questions.
Yes, I do. Okay, thank you very much for this nice presentation.
Yeah.
Excellent.
I repeat, dear JP, thank you very much for this nice presentation. I really enjoyed and also saw your gradual progress in your PhD. So I have actually a question too, which you already appears in the title of your presentation and your thesis, where you use the term molecular clusters, implying that the clusters have a molecular character. While I agree to that to a large extent, can you tell me what's the difference between a molecule and a cluster?
I mean, in the end, we're looking at the clusters all the way from individual monomers to basically crystalline structures, right? So at some point, in between that, it stops being a molecule because it is part of a solid. Where exactly that is, like what cluster size that is, can't really say, but I would say that is the difference. I said molecular clusters mostly because I treat them as molecules throughout this thesis. But yeah, if we go big enough, I would argue they stop being molecules.
So I understand from your answer, it's essentially also the size that determines this. So maybe this is a mean follow-up question, but what do you say to chemists that say the C60 Buckminster fullerene is a molecule, but the TiO2 dimer is a cluster?
I mean, everyone's entitled to their opinion.
No, I'm coming then to my second question. Actually, you introduced also in the talk, and I read in your thesis about the non-classical nucleation approach that uses not top-down derived data, but really the actual cluster data. Maybe you can also compare this non-classical nucleation approach with a chemical kinetic approach. What are there the major differences?
I mean, it is very close to almost equilibrium chemistry, which would be a rate approach, where the forward reaction and the backward reaction are about the same. So they are definitely quite similar. I'm not entirely sure which differences you want to hear about.
Oh, well, I was just thinking maybe chemical kinetics also looks at non-monomeric additions, so maybe having
like that is the big caveat to pretty much both, one of the big caveats to especially to all the nucleation approaches that I looked at in this work is because it only uses homogeneous molecular growth, which means whenever you want to grow your cluster, you add one more monomer. So for size 3, add 1, size 4, size 6, add 1, size 7, size 12, add 1, size 13. But obviously these exist in parallel, and there's also you can have collisions between a cluster of size 4, cluster of size 6, boom, cluster of size 10. And for that you would need then a full kinetic rate network with, which is a lot. And some of my colleagues working on that.
I agree, and you could even extend it more and saying a dimer and a tetramer gives you a pentamer and a monomer, and then you increase
absolutely.
massively.
In the end, there's the dimensionality of it just becomes a bit difficult to handle.
Absolutely, I agree. Then another question I had that was more related while reading your thesis. You referred in the nucleation approach also to an A0 as a theoretical radius of the monomer. And I was wondering what is the geometry of the TiO2 molecule or monomer?
So now I'm very sad that I didn't put the figure in my bonus slides. We actually did some investigation on that, basically how you look at the radius of these the clusters, also of the monomer, because in the end, this is the radius that determines collision rates. This is the radius that determines how fast it grows. So this is the radius that should be an interactive radius rather than just like geometrical physical radius. So in general, I think that was a study done in Copenhagen. They what they found, but we tried different approaches. So basically, we basically just approximated it as a sphere, or we added van der Waals radius to that to see if that change in effective radius has a big impact on nucleation rates, and it does not. So just approximating it as a sphere with a radius, I think it's 2 angstrom, is a good enough approximation.
Okay, yeah, that explains why the bond length in TiO2 is smaller than this value of A0. But then maybe just to clarify, so the TiO2 molecule or monomer is not a real sphere.
No.
Okay. Thank you. And then pretty much the last question that I have, that you mentioned in section 3.5 of your thesis, and actually it fits up also to the previous questions on the spectra that we've heard, that you mentioned that TiO2 and SiO are the most likely high temperature condensates and nucleation species. Can you think of any other species?
I mean, Al2O3 is also pretty stable at high temperatures. I think the next ones, things like magnesium oxide, GeO, it's been looked at. Vanadium oxide also stable at high temperatures. Like there's a lot of it's mostly metal oxides.
And then my really last follow-up. So could you imagine that like also mixed metal oxides like alumina titanates or silicon titanates could play a role?
You mean like could nucleate, could form these?
Yeah, so sort of heterogeneous.
Yeah. I mean, that like it's definitely possible. I don't see anything speaking against it. The question is like if you really want to open that box of kinetic rate networks and isomers and different species, because that is a lot.
Yeah, I agree. Yeah. Thank you.
Thank you very much. Next is Professor Christopher Wilkins, but is not present with us. And then we have Jeremy Harvey, who is also not present. He had a conflict of schedules, but he did send me some questions for you, 4 of them. So maybe we can start with the one about the spectra, because that's what we were discussing here. He asked me to ask you, as you mentioned, for example, in the first paragraph of the discussion section on page 93, under some pressure and temperature regimes, you predict that the most stable clusters is the largest one, or sometimes the one just smaller and equals 14 or 15. So that in reality, much of the TiO2 may be present in the solid phase.
Yes.
Can you comment on the spectral properties that you would expect to see in the regime where large clusters and the solid are present?
I can take the easy way out and say if the solid is stable, we probably have enough nucleation to form clouds, so we don't see anything. Other than that, I mean, the spectral properties of the solid phase are pretty well studied. So, like, if, thing is, obviously, since I didn't include full condensation with a solid phase, I don't have abundances for the solid phase, and kind of like it's difficult to just gauge from the abundance of Ti15 how much would be then solid phase. So like if we had the abundance of the solid phase in there, adding that spectral data would be not an issue.
Okay, maybe I will reformulate the question from my understanding of the question, and I had similar questions myself. Given that you don't know what happens for larger clusters, can you actually suggest an observation based on your results, or is this purely theoretical? Because since you are missing larger clusters.
Yeah, this is this is the cluster data as far as we have it, of course. So yeah, this is theoretical because larger clusters would probably take away definitely from the TI-15 structure. But there's also, we can't know for sure until we go to larger clusters if there maybe also is an area where TI-15 is the most abundant and the larger clusters will not be as abundant. So I can't say for sure. Intuitively, yes, these are purely theoretical, and for lower temperatures, there will be larger clusters that have different spectra.
Okay, thank you. And then some questions about chapter 3. Obtaining accurate predictions with quantum mechanical methods often relies on beneficial cancellation of errors when comparing different systems. So you are measuring an energy difference, essentially, or calculating an energy difference. Error cancellation, for example, for binding energies, which is what is most relevant for you in this chapter, occurs most favorably when the two fragments coming together to form an assembly and the assembly itself all share a rather common electronic structure. When forming titanium oxide clusters from titanium oxide fragments, the nature of error cancellation is likely to be different than when forming TiO2 from titanium and oxygen atoms. Can you comment on this in the light of your results?
So wait, the error cancellation is usually favorable when it is made up from the atoms or made up from the monomers. What was the...
Well,
I'm just trying to understand the question correctly.
When the features of the two either atoms or monomers that form a larger monomer are similar, then you expect to have a cancellation of error. But that might not always be the case. And I think this is related to the question before on what is the distinction between a molecule and a cluster in a way.
So you mean the the monomers that are part, for example, of the dimer are structurally different than just individual monomers. Their bond lengths change, their bond angles change. So so they're different from TiO2, from the monomer which I based the DFT calibrations on. Yes. However, I don't really see another way. There is no laboratory data for clusters of size 2 and 3 that we can also look at, also calibrate on. So laboratory data for the monomer, for the individual molecule, is all we really have. So pretty much we did the best could with the data that was there. But if experimental data, especially for cluster size 2, size 3, would exist, that would be very beneficial in calibrating this.
Okay, thank you. And then also in chapter 3, you write, when you discuss the functionals that you use for the DFT calculations, I note that the use of an empirical dispersion does not originate from a physical or chemical consideration, as these corrections improve the accuracy of van der Waals interactions, and the effect of these interactions in molecules of the sizes considered in this work is not significant. Is this correct? And have you compared the binding energy of N titanium oxide molecules coming together to form a cluster of those molecules, as calculated both with a non-dispersion corrected DFT and dispersion corrected DFT?
I haven't. That sounds like a very interesting thing to look at. The empirical dispersion thing was something that he set me on to.
Okay.
I had a lot of talks with him about DFT, and he suggested using it. And we had a referee who was like, "This is not how it's supposed to be done." Since we did look at the calibration onto a single monomer, where like van der Waals forces are basically not relevant, the empirical dispersion there shouldn't have played any role. It would be very interesting to look at larger clusters to see if their empirical dispersion does make a difference for the assembly of a cluster from its constituent molecules.
Yeah, for clusters, it will likely have a big impact, I think. And finally, last questions. You use as a best method to calibrate your calculation the CCSDT, the Pepper cluster with single, double, perturbatively triple excitation method, which you call the gold standard of quantum chemistry. Yeah. Yet this gives a very large 90 kilojoule per mole error for the binding energy of TiO2. Can you comment on possible reasons for this discrepancy?
To be honest, I am not an expert on coupled cluster systems. That was something we did in order to see if there maybe is an option to get something that's very high level for cluster sizes 2, cluster size 3. I do not know why the deviation is so large. I don't know if the parameterization was off. Like this is don't know.
Okay, yeah, I can tell you that something is definitely missing. Maybe that some electrons are not correlated or something like that. But
it could also be
such large errors.
It could also be that the experimental data is from the anaphorist tables, which were mostly computed and measured in the 70s. I have colleagues who have already seen. For different molecules have seen pretty big discrepancies between all of the calculations and the data. So it is possible that the data isn't the best, but still 90 kilojoules per mole is a pretty big error. So yeah.
Okay, thank you. Next is the co-promoter, the co-supervisor, Christiane Helling. Do you hear us?
Yeah, I perfectly hear you. Jan Philip, first of all, thank you for your nice summary of all the work you have done and the path you have walked with us through this really challenging project. I would like to bring this back to the astrophysics part and astrophysics perception. So in exoplanet sciences, we have two branches of how to deal with observed data. One of them is called retrieval and one of them is called forward modeling. Now, I would like to take us a little bit into the retrieval method to formulate my question. The retrieval approaches do apply a very, very simplified cloud parametrization, which we often call S equals 1, which is basically looking at the thermal stability in order to decide about clouds. And my question for you is now, why should we go through the efforts that you have conducted during your PhD thesis if there is such a beautifully simple approach that we are calling thermal stability? So what is the qualitative difference and why?
Well, the qualitative difference is it's pretty much what we can see in our work in the comparison between modified classical nucleation theory and non-classical nucleation theory, because similarly MCNT has a requirement for the super saturation ratio to be larger than 1. So S equals 1 is like a requirement for that. However, if you look at the full cluster data, you can have these clusters forming even when there is no supersaturation. So you can form them even earlier than thermal stability, than that thermal stability criterion. So if you have these like precise cluster data all across all sizes, you can potentially see places where the clouds go higher up because they already start above their thermal stability.
All right, let's dig a little bit deeper. I want to hear from you the S=1 approach. What does it mean? So what does thermal stability mean, and what does it not allow us to calculate?
So S=1 means the supersaturation ratio is 1. So basically, there's more of a certain molecule in the gas phase than would be in equilibrium. So some of it needs to transition into the solid phase. So that's what it does. If you go above S=1, you have a solid phase, and in addition to the gas phase. So that is just a very strict line. So yeah, that doesn't allow us to go into areas where S is smaller than 1.
All right, let's go on to another question then. Thank you. So David, I think, has alluded to this, that in astrophysics we have very complex, chemically very complex gases. And TiO2 is admittedly one of those who are not very abundant, in contrast to SiO. So if I now have my gas, a box of gas, which is just made of this huge amount of SiO and little TiO2, and I cool this down, and I know that my cloud formation needs condensation seed and surface growth, which of these materials is the dominating nucleation species, and why?
At higher temperatures, TiO2 is dominating. So it's dominating in as a nucleating species. So you will have the condensation seeds formed from TiO2. The SiO can then condense on these condensation seeds and make up the cloud particles.
Okay, can you say a few words about element depletion?
I mean, if we start from equilibrium chemistry considerations, then there shouldn't be any element depletion. Like it's not like there's too much. Like you're not depleting oxygen because you use the TiO2 to form condensation seeds, because that oxygen is already bound in silicon oxides. But yeah, and like you deplete the TiO2 because you use it to build your condensation seeds.
Okay, thank you. I have one last question, if I may. So you told us that it's important to know the local temperature and pressure in the atmospheres, and then you moved on to tell us about the absorption cross sections and the opacity, basically. I would like to know from you in which way the temperature and then also in which way the pressure affect the nucleation rate.
So the main way they affect the nucleation rate is, first of all, the growth timescale, because in the growth timescale talks about how much collision there is between the clusters and the monomers that need to be added to them in order to grow. And the velocity distribution of the gas is given by the pressure and temperature, by the Maxwell-Boltzmann distribution. And of course, the pressure also influences the number density, how much there is, how much collision there is. So that is the main, that is one part of how pressure and temperature influence that. And of course, on the other side, with temperature, you have the thermal stability of the clusters. The Gibbs free energies of formation are dependent on the temperature. So those are all factors that play into how to calculate the nucleation rate.
Okay, thank you.
Thank you very much. I now turn to the supervisor.
Thanks, Jeremy. Thanks also, Jan Philip, for the very nice presentation. I would like to end also with a few questions, and I will start at the last part of your thesis, and then I will go to the beginning, if that's nice, if that's good for you. And I start with the previous discussion we just have had. I think it's the figure on your slide 42, and it's figure, yeah, I think it's slide 42. Yes, that one. So we have already discussed that potentially the ones that you now have in the orange ones, that could be the signature of their forming solid species. Yeah. But does this then also imply that what is now in that light pink, so the monomer, the TiO2, would just vanish? Would we be left with any monomer? You know, now you stop your calculations, but going to the solid state species implies that we need either building blocks that are monomers or that are larger in cluster size.
So what this graph shows is only the most abundant TI-bearing species. That doesn't mean that there's no TiO2 in any of the other areas. So there still is TiO2 in order to grow. What you can see if you basically take a slice through here is that basically the abundance of Ti15 here is roughly 1/15 of the abundance of TiO2 here.
Yeah.
So basically all of the TiO2 is just in Ti15. So there isn't it doesn't vanish. It just like becomes part of the cluster. Like obviously there's no active nucleation rates happening here. These are all just equilibrium chemistry considerations.
Mm-hmm. And if you now look at that plot, can you roughly tell the public what James Webb would observe? First of all, what pressure ranges are probed by the James Webb Space Telescope? Secondly, if you would take that to the prediction level, what parts per million, how much would you expect the change to be? And is it then observable with James Webb or not?
That would be a very interesting question to answer. First of all, for the pressure levels that we're looking at, so that is very dependent on the target we're looking at, but and also if it's cloudy, if it is not cloudy, but usually I would say somewhere around 10 to the -4, 10 to the -8 would be a pressure level that should be observable. Sometimes down to 10 to the -2. It, as I said, it varies very much depending on the target we're looking at. And then, like said here, like these are total absorbances that are put onto the spectrum at that certain pressure level. As I said, I don't have any comparable absorbances for the other for other species in there. So with MIRI, we could this is the wavelength range that would be observable. So if there is the especially the part that's contributed by the second largest, by the Ti14 cluster, I think would be is very interesting and could be observed. Does that answer your question?
Yeah, it does. Thanks. Then my second question links a bit also to what Jeremy Harvey has been saying. Since at some point, I think it was slide 31, you mentioned the value that you have derived for the binding energy. And now I just was hearing also that when it comes into titanium dioxide, that there is an uncertainty of 90 kilojoule moles. Here you see they mentioned a value of 10,000 roughly kilojoule per mole. What is the uncertainty on that value?
0. No, it is basically I think roughly for the NFNIST values, I've always heard that the uncertainty is roughly 4 kilojoules per mole per monomer unit, and like the DFT calculations don't give you error bars. Mm-hmm. So it is very difficult to say. As you can see here, like the difference to the formal aluminum is only 6 kilojoules per mole. I would say that it's definitely within the error bars. Like these two isomers are probably quite. I would use a slightly different parameterization of the DFT. A different molecule wins out, different cluster wins out. So I can't make exact comments about the accuracy, the precision of the data. So I think for this, on the order of 100 kilojoules per mole, is accuracy. Like I think it was 4 kilojoules per mole per monomer unit, basically. So that would be 4 times 13. So 72. Yeah.
Okay, good. And now my last but one question. So we always assume that these global minimum candidates are good proxies to play the role as key species there. Is that a valid assumption? Don't we just wouldn't you expect a kind of an ensemble of candidates?
Like the there's a question about relaxation times. I would say, like if you if there's a if you have a cluster of a size and you add a monomer, you now have a cluster of the next highest size, and given enough time, that will most likely relax into the ground state, into the global minimum structure. Of course, if you are in a very turbulent, if you have lots of collisions going on, if that doesn't have to happen. So it's very likely that also some of the other isomers exist in in actual physics, in real life. So yeah, I mean, that's also why I calculated all the isomers for all of these sizes, so that we can look at different isomers participating in this nucleation process.
Okay, good, thanks. And then one of the first slides, but I forgot to write down the number. I think it will be 10 or 11. It was the slide where you have shown the Kreitberg observations. I think it was whatever was number.
There we go.
Yeah, that one it is. Okay. You have explained to public that this might be clothes. But this is not what you see there depicted. You see there are people playing with more water, more CH4, so higher metallicities in general.
Mm-hmm.
Can higher metallicities mimic a spectrum that has clouds? And yes, if yes, why?
I know that they can. I know that higher metallicities usually produce less pronounced spectra. Why? Can't give you an immediate answer why. I mean, high metallicity means less hydrogen, so overall higher mean molecular weight. I would assume that the atmosphere is just more dense, more condensed a little bit, and therefore you don't see as much atmosphere until you reach time equals 1.
That's it. Indeed. Thanks.
Thank you. I have some questions myself. So first of all, let me say that you gave a very nice presentation, and I also enjoyed reading your manuscript. Although small criticism, I think you could have been more extensive on the comparison with previous theoretical work, because on TiO2 clusters, which is really the core topic of your PhD, you give a few references to previous works, 2, 3 maybe, but there's actually a huge amount of literature on those clusters because they also appear in a completely different setting. I don't know if you see what I'm talking about.
Like, I mean, I mostly looked at clusters in the context of like formation in gaseous environments. I'm pretty sure they form on surfaces of, is it semiconductors or not? Like,
yeah, it's related to that indeed.
It's related to that, yeah.
So titanium oxides are also semiconductors. They have a band gap. You can try to control it. You can use it for photocatalysis, etc., etc. So there's plenty of data on those clusters, the energetics, the geometries, etc. So it would have been nice to have some comparisons with those results. But that's just a comment. Now, some general chemistry questions about what you did. So what you assume equilibrium chemistry, is that true? Always?
No. So of course, like you need to be collision dominated in order to have equilibrium chemistry, and especially if you go. It's going to take a while. I'm just going to keep talking. So if you go through this and you look at especially the higher altitudes, there you don't have enough. There the pressure is too low. You don't have enough molecules going around.
Okay.
I'll get there. Here we go. Okay. So yeah, especially like here at 10 to the minus 12 bar, very, very low pressures. I'm pretty like equilibrium chemistry is a very, very bold assumption in those areas. But if you go lower down to 1 bar, 10 to the minus 4, even I would say I think you can make an argument for these spaces being in chemical equilibrium, and there's work being done in our research group on non-chemical equilibrium nucleation rates, things like that.
Okay. And then TiO2 in itself, where does it come from? How is it formed in space?
From a titanium and 2 oxygen atoms. I mean, it's like I would say it is like from equilibrium chemistry. There, I'm not entirely sure about formation pathways for TiO2. I mean, we know that TiO is quite the abundant molecule in space. Like it is what it's for one of the characterizing spectral features for some M dwarfs, for the LT dwarf transition. So TiO is quite abundant. So yeah, oxidize the TiO and you have TiO2. And I would assume that's mostly where it comes from. Otherwise, I'm not really aware of formation pathways.
Okay. And then you argue at some point, I think it's on, I noted page 63 of the manuscript, that titanium dioxide is the most abundant Ti-bearing molecule.
Mm-hmm.
And yet that's not what seems to come out of your models. And also, it has never been observed, whereas, for example, TiO has been. So why is that?
So TiO2 is like, according to equilibrium chemistry considerations, without putting the clusters into the equation. So if we just look at all Ti-bearing molecules, and then for pretty much everything that is not TiO, everything here is just TiO2. So the argument that I'm making is that TiO2 is the most common Ti-bearing molecule for most of the temperature pressure range that we're interested in. It hasn't been observed in any, but that is also because like TiO2 has been indirectly inferred in some exoplanet atmospheres with cloud cover and potential for TiO2 trapping further down in the atmosphere. But yeah, usually it is too far down in the atmosphere in order to be observed. So that's why it hasn't been yet.
Okay. And then to come back to the issue of isomers, because that's a big problem. You realize that, I'm sure. I don't think you reported the energetics of these isomers. So how stable are they compared to the global minimum?
That varies a lot. There are some sizes where the top 3 isomers are only a few tenths of kilojoules apart. I think that's the case for size 12, for example. And there are some where there's a gap of like 150 kilojoules from the lowest isomer to the next. So it varies a lot in between the different sizes. But yeah, overall, like all of the data, all of the thermochemical data can also be found online. So if you want to look at it.
And so how would you model a full spectrum, including all these isomers? How do you know the population of each isomer?
So for the way GGChem works is that it approximates the Gibbs free energy independence of temperature with a it's not a polynomial, but like something similar to a polynomial. And I modeled this polynomial for all the isomers. So all the isomers are in the equilibrium chemistry code. So the abundances come from that. So yeah, while you see here TI14028.0, like also here is, for example, TI14 or 281 or 282 or 283, etc. Like the next couple of isomers, obviously they're way less abundant. Sorry, they are they're less abundant, so they don't show up in the most abundant graph, but they're in there, and they're also part of the spectrum.
So you consider them independently, and then you add up all their contributions.
Yes.
Okay. Okay. Thank you very much. I think that's everyone. So now the jury will deliberate. Ladies and gentlemen, dear colleagues, I will now proclaim the result of the deliberation by the examination committee appointed for granting the doctoral degree in science physics. Jan Philip Sindel has presented to the faculty his PhD on the topic Cloud Formation in Exoplanet Atmospheres, Nucleation of Small Molecular Clusters, in partial fulfillment of the requirements for the PhD in science physics, and he has now defended his thesis in a public session before the examination committee. The examination committee has determined that all requirements concerning the granting of the doctoral degree that are prescribed by the law and by the university regulations have been met. Therefore, on behalf of the rector of KU Leuven, I confer upon Jan Philip Sindel the degree of Doctor in Science Physics. I close now this session. I need your signature here. Yes. Thank you. And in exchange, you receive this certificate. Yes, it's temporary, but that's what you get now at this point. And before ending the session, I would like to pass the word to Lane and David, who would like to say a few words.
Just a few. Yeah, dear Jan Philip, it took us some time to come back. We were closed out of the chapel, so we couldn't enter anymore. We even couldn't otherwise have granted you the PhD without being able to do that. Now, I'm honored to be here today as one of Jan Philip's supervisors, together also with Christiane, who is still listening to us online. And now, as you may have gathered from Jan Philip's presentation and the questions asked by the PhD, Jan Philip's research has focused then on the nucleation of titanium dioxides using quantum chemical calculations. And, you know, that has already been a challenge, since you could also hear from his presentation that Jan Philip is bridging different disciplines from astrophysics to chemistry, and doing such an interdisciplinary research is not obvious. It has taken us, my colleagues, also together with David, some time to see how we could best do such a research. And then often as a student, you enter the field and you think that you will, for instance, immediately work on exoplanet data, but there is so much other groundwork to be done that is so much of importance. And the results shown also to us today, you know, we have gotten various questions. Can we now observe that, you know? And this data we have them literally on my desk. We see spectral features, and we cannot yet tell to you, the audience, since we have an embargo, but also in general, you know, what are the species we do see here now? And can we indeed say something on cloud formation, since then that has then that big impact on our next step, the understanding of the potential habitability of planets and their atmospheres. Now, Jan Philip, your journey has been quite extraordinary, since you have first started here in Leuven, then you went to St. Andrews, at least we thought so, but finally you ended up in Graz. This was not our plan at all. So doing your PhD in 3 places, you know, given already a discipline that is bridging various fields, but then going to 3 places, it takes a lot of energy. We have realized that, you know, you always have to move, you always have to adapt to another institute with other habits. Yeah? And also for me, Jan Philip is the first dual PhD that I'm granting, and there are various other people in the room who potentially will achieve that also in the future. Now, Jan Philip, you have set quite a standard to do so, so I hope also for you here in the room, you follow the same footsteps. Since such an achievement is not without challenges. Jan Philip, we have to navigate to different academic systems. Even this morning, I was not sure that we were following the correct procedure to do it all. You had to adapt to different PhD supervisors. Now you have overcame all of that with very great success. And that has also asked you quite a bit of perseverance and hard work. Now you have published your work already. One has already been published in the literature. The other one is submitted. And then you have also contributed to other papers as co-author. Now, these are in that field of astrochemistry. So you have bridged that with great success. And this is also for some of you, I know you are a bit out of your comfort zone since we have been discussing quite a bit of chemistry today, but I just can advise you, read the first chapters of his PhD thesis. I would like to offer them to you, but he can do that online, I guess, since he has given a great introduction to the field of chemistry, very well readable, so that you can understand, what is the limits of our understanding, but what we can achieve, what you have achieved, and also what we can do in the near future. I'm just talking. And now, on a personal level, but that will be more addressed later by David. I remember one of these most striking moments when you entered the coffee room and you had your first, maybe just a new one, tattoo on one of your arms. We cannot see it now, but still today I'm wondering what is the meaning of that one. We have been discussing that and how the colors and but I don't know the meaning. It has been a pleasure to work with you, Jan Philip, over the past few years, although now the last 2 years we haven't seen at all each other, owing also to COVID and you being somewhere else in Graz or in St. Andrews. But I'm proud that you could defend it here today. A second time, we have been quite dedicated also in our questioning again today, going again from astrophysics to chemistry. So in conclusion, I would like to congratulate you with your incredible achievements and wish you all the best in your future career. We just even have been discussing with Christiane what that career could be, but you shouldn't listen to us. Jan Philip, we are proud of you and we cannot wait to see what you achieve next. And now I'd like to give the microphone to David.
Thank you, Lynn. Dear JP, I remember in 2018 we met for the first time in person, and I believe it was a special day for both of us because you just started your PhD studies in this historical and prestigious university. For me, it was also a first experience since you were my first PhD student that I advised from day one onwards. And so it was a real pleasure for me to introduce you in all this weird, complex world of computational chemistry and to see your advances that gradually took place in that field. And now I meet you as an expert in force field and tight binding methods in DFT, and it's great to see. And moreover, I experienced you as a very sociable and very active fellow, actually, participating in various sporting activities, including badminton, basketball, and volleyball. And I only mention a few of the sports that you actually did. And one special memory that I have was this blacklight volleyball tournament in Flimmeren, which is, for those who don't know, that is a quite remote place in the Kemper. And although we didn't succeed to go into the finals, we won the award for the best dressing, actually. And I think that was also owing to a large part because of you. And since we celebrate your graduation today, I would like to hand you over another trophy.
This is the real winner's trophy from Blacklight Volleyball in 2020 in Flimmeren. Best verkleide ploeg. I definitely mispronounced that. Thank you. That means it's my turn. Thank you. Yeah, first of all, thanks to all three of you. Thanks to all of the jury members who joined online. Thank you, Christiana. Doing a PhD at, as it turns out, 3 institutions over 4 years during a global pandemic, it's not the easiest thing to do. Overall, I would like, first and foremost, say thank you to all of my colleagues in Leuven and St. Andrews and Graz as well, because the great thing about doing a PhD is you're not doing it alone. You have your peers, there's a lot of people alongside you who are going through similar struggles, have similar issues, and at least in Leuven and also in St. Andrews and Graz, I have found that the solidarity between the PhD students here is absolutely incredible. And so yeah, I'm very happy to see a lot of you again, also for the first time. Thanks for coming. And so yeah, that's all I wanted to say. Huge thank you to that. And then, of course, David Lane, thank you so much for all the invaluable advice that you've given me for, being there when I needed someone to talk to about science, but also but other stuff. I never had the feeling that there was anything I couldn't talk to you about. So I really appreciate that. And I would like to thank you with a little gift. Right. Oh. This is excellent to do with a microphone in hand. So, Elaine, thank you very much. Oh. Hope you have more hands than me. Wonderful. Thank you so much. And David, I unfortunately don't have a trophy for you, but I hope. Okay. All right. Thank you very much. So yeah, thanks everyone for coming. And I'm pretty sure a lot of you are already hungry and eager for the reception. So I think with this, thank you all so much for coming. And there will be a reception upstairs. Please find me there. All right. Thank you.